Now with these secondary active transporters, we'll take a look at what happens if you affect your energy source. So here we're looking at another example of a secondary active transport process. This is the lactose transporter. With the lactose transporter, it is going to use the proton gradient in order to, that'll provide the energy to transport lactose inside the cell. And that's very similar to the sodium glucose symporter we were just looking at. Well, the proton pump is responsible for providing the proton gradient that's used as the energy source. So if we in any way inhibit the proton pump, if you look at the graph here in the bottom right-hand corner, the red shows just our active transport process. Notice you do see the saturation kinetics occurring in this process there. If we either add a small molecule inhibitor of the pump, such as cyanide, or if we mutate the pump to something to a basically mutant that has lower activity, what you can see is that our lactose transport is going to be decreased. So that's what you're looking at in both of those examples. So if you do anything to alter production of this proton gradient, you will inhibit your lactose transporter. So no gradient leads to no transport through the secondary transporter. The last type of transport that we'll look at is transport through ion channels. So transport through ion channels is much, much, much faster than transport through some of the facilitated transporters we were looking at, like the GLUT transporters or the symporters, antiporters that we were looking at on the previous slides. So with the ion channels, what we're going to need to do is we start off and we have a hydrated potassium ion in this case. The water molecules are going to have to be removed from that potassium ion, stripping it down to just the naked ion that combined in the channel, and we have these alternating ion binding sites. What happens is there's going to be charge repulsion between the neighboring potassium ions that's going to propel the ions through the channel, and then once it's through the channel, it'll be rehydrated with the water molecules that are available inside the cell. So this is thousands of times faster than transport through transport proteins. So if we want to look at how the ion channels achieve their selectivity, what's going to happen is that there is a desolvation energy associated with removing the water molecules from the hydrated potassium ion sphere prior to binding in the ion channel. However, once the ion binds to the channel site, the amino acids are located in such a position that it's going to mimic the original hydrated potassium ion. So the resolvation energy that we achieve upon binding to the site inside the channel is sufficient enough to overcome the desolvation energy that was lost upon removing the water molecules. If we want to contrast that with sodium, if sodium were to try to get through the potassium ion channel, what happens here is we also have that desolvation process that occurs with the sodium ion prior to binding to the binding site in the channel. If these ions are hydrated, they're too large to fit through the channel, so that water's got to be removed at the start. However, since the sodium ion is much smaller than potassium, you don't get maximal kind of resolvation when that sodium ion binds to the potassium ion binding site. Therefore, this favorable resolvation energy that we regain isn't sufficient to overcome all of that desolvation energy we lost upon removal of the water molecules. And therefore, you're going to see much higher selectivity of the channel for the larger potassium ion compared to the sodium ion. Now, our ionophores are going to work very similar to the ion channels, except in this case, these are going to be really small, almost mini portable ion channels, where the ionophore is going to surround this is a potassium valinomycin. Valinomycin is the ionophore complex, so that's going to mimic the hydrated potassium ion, giving it that favorable energy that's going to allow it to transport potassium across the cell membrane. And again, remember that these are going to go in whichever direction is preferred by the electrochemical gradient. So one last slide here to try to summarize most of what we've talked about. Starting at the top with the transport of glucose across the cell membrane. So in this example, the glucose is going down its concentration gradient. So this is an example of facilitated diffusion. We do not need any additional energy source. Once the glucose gets inside the cell, it can undergo glycolysis through the citric acid cycle, oxidative phosphorylation, resulting in an increase in the concentration of ATP. This increased concentration of ATP causes the ATP-cated potassium ion channel to close. And when this occurs, we are going to then open the calcium ion channel, leading to an increase in our intracellular calcium ion concentrations. That then allows for the granules containing insulin to go to the surface of the membrane, where we can get insulin secretion through exocytosis. Now, just to point out, we did use, in this case, ATP in order to close the potassium ion channels. However, this is not an active process. Remember, if we have something that's gated, it's just the presence of the ATP causes the gate to close. The ATP is not hydrolyzed or consumed, so this would still be going. That process is not an active process. It only occurs based on the concentration gradients. The other thing I'd like to bring in here would be the valinomycin, which is the potassium ionophore. So recall that ionophores transport ions going down or with the concentration gradients. So in this example, the presence, if we added valinomycin into the mix here, its presence would have the same effect as opening the potassium ion channels. So if we were to add valinomycin, what we would then expect is to have a decrease in the secretion of insulin, because it will essentially have the same effect as opening that potassium ion channel. So that about wraps it up and summarizes everything you need to know about membrane transport.